Okay, so a skydiver falls through the air at one instant of time. The air resistance force on the skydiver is 30% of the skydiver's weight. What is the skydiver's downward acceleration? Draw a free body diagram, write a Newton's second law equation, and show the process of solving the equation. All right, first things first. This 30% thing, this seems kind of confusing. So it's 30% of the skydiver's weight. We know that the skydiver's weight equals mass times acceleration due to gravity. We also know that the air resistance is 30% of this. So we'll just convert 30% to a decimal, and it's 0.3 times the weight. Okay? There, we got that taken care of. Next up, let's draw a free body diagram so we can figure out this downward acceleration. At one instant of time, the air resistance is 30%. So if this were on a grid, then you would want like this to go down 3 for the weight, and then this to go up 1 to show that it was exactly 30%. Write a Newton's second law equation. All right, so we have the net force is the stuff that makes it go. What's making it go here? The bigger vector, the weight, minus the stuff holding it back. The air resistance equals mass times our net acceleration. Okay, so we've already got this stuff up here. We have mg, and then we have 0.3 mg equals ma. We have a mass in each term, so we can divide out mass to solve for acceleration, and that'll get rid of that. And what we're left with is acceleration equals g minus 0.3 g. And if you want, you can just substitute in here 10 minus 30% of 10, which is going to be 10 minus 3. So we have our acceleration of 7 meters per second squared. Circling the answer. Okay, not too hard. Okay, the next one is definitely a little bit trickier. A skydiver jumps off a building at t equals 0, deploys a parachute at t equals 4.8 seconds. So that's what's happening here on the graph. The upward force that the air exerts on the skydiver parachute system is F. The graph shows the downward speed as a function of time, so velocity as a function of time. Rank from strongest to weakest values of F. All right, so first thing we have to know that A equals the net force over m, right? So these two are directly proportional. So wherever our greatest acceleration is going to be where our greatest force is. Make sense? I hope so. So we are going to look at 1 second, 4 seconds, 5 seconds, and 8 seconds. At 1 second, so we've got this one. At 4 seconds, here, how are we going to get acceleration from a velocity versus time graph? 5 seconds. And finally, 8 seconds. How are we going to get acceleration? Right. We are going to use the slope. So all we have to do is figure out what's going on with the slope at these points. I've brought out a ruler, but you can use the sheet of paper. Just fold up the corner. That way you can see a good tangent line. And the tangent line is going to let us assess the slope of a curve. So, okay, give me this thing. And I don't think I need a tangent line for that. Well, take it easy there. Take it easy. All right. Oh, I need my pen. tangent line here. This is a 0. This looks like a 0. And then we have that last one on that really steep point, right? Oh no, I gave a hint away. It's a really steep point. It's not a good hint, but a hint nonetheless. All right, now looking at it, we should be able to rank this in terms of strongest, or from strongest to weakest force. So we're going to do that by looking at our acceleration. Slope of velocity versus time graph is acceleration. So we have the slope for this one. Okay. Flat, 0, 0. So we know 4 and 8 are equal to each other. Which one's bigger, 5 or 1? That's right. 5 is. 5 is bigger. F5. Steepest slope is greater than F4, which is equal to F8, which is greater than F1. That's how I see it. What do you think? I think we have to explain our reasoning. And that explanation starts off with the slope of velocity versus time graph is acceleration. We also can note that the job of air resistance is to resist or slow down objects in free fall. So, using Newton's second law, mg minus F air equals mass times acceleration. Stuff that makes it go minus stuff holding it back equals mass times acceleration. And then we solve for air resistance and we get mg minus ma. What this tells us is the lower number acceleration, the greater the air resistance. F5 has the steepest negative slope, so the air resistance was slowing it down the fastest. So air resistance was the greatest. Okay, that's what I mean by this problem being a little tricky, because it instinctually you're wanting to say, wait a second, F5 is the steepest, so it's moving the fastest. But remember that it is slowing down. This is a velocity versus time graph, so as we get lower and lower and lower, our velocities are decreasing. So our net acceleration is going to be small because we're not speeding up due to gravity. Instead, we're actually slowing down because of air resistance, and that's happening at F5. Meanwhile, F1, the velocity was actually increasing, so the air resistance was not doing its job. That's it.